Awesome. Sush, would you like to introduce our speaker today?
Yeah, very excited to have Suhas today. He is currently doing a PhD at Stanford, and before that, he was also at CMU, where he was finishing his undergrad cum masters. Worked with Aditi once again, so we have another student from the lab. He's also worked with Christina. Like we've been in the same lab for some time, and he's worked on some very relevant work, things in the recent past, something on synthetic data and how you can keep improving, self-improving models with their own synthetic data. I think what today he's talking more about is how to adapt to rare domains, which is very relevant to some of the work on curriculum training, pre-training, or fine-tuning the conundrum that we've been talking about. So very excited to learn more from his investigation.
Yeah, cool. Thanks for the introduction. Nice to meet you all. Yeah, so I mean, I'm Suhas. I worked with Aditi and Christina in undergrad, and they were very helpful and taught me a lot about research when I was young. So glad to give the talk now. Cool. So today I'm planning on talking about how to adapt to rare domains. So we can just get started. So the brief motivation is that the current paradigm for training is that you have a lot of like internet data, which we're going to refer to like as common data, which is data that you just like pre-train over, and you kind of just do this in any way. You just order it and you continue pre-training, and you get a really good pre-trained model. But unfortunately, this pre-trained model is like very good, but unfortunately, it's like limited in that there are usually only like a few documents that you like actually care about performance on. So there's usually some downstream tasks that you care about. So for example, that could be like being really good at coding or math or following instructions. And you have like a small number of like curated documents that you like care about for this specific task, but you only really care about performance on this task. So the motivating problem throughout this talk is that you have this like small amount of rare data, and it is some like finite resource. You kind of can like only use it in like a couple of different ways, but you need to use it as well as you can in relation to like your pre-trained model to get the best possible performance for this rare task. So today's talk, we're just going to go over like two simple ways in which you can actually use this rare data to get better performance. So the two approaches, we're probably going to spend a lot more time on the first approach, is talking about how to order your training data. One thing that people do in practice a lot is that if they want to get a lot of value out of this rare data, they'll maybe bias it, put it closer towards the end of training, do things that look more like fine-tuning rather than just mixing it in uniformly into the pre-training data. And this is one way in which you can leverage your rare data better. And a second approach that people use is that they try to generate more rare data. So maybe this is along the lines of synthetic data. They try to generate more data that looks like it to continue improving performance. Yeah, hoping we can be relatively informal, so feel free to like interrupt me or ask any questions. We'll try to walk through both of these projects over the course of the day. Cool. So the first project we'll be talking about is how to order data. This paper should be on arXiv, but it will be up there soon. This is my advisor, Percy. So I think the first simple question that you can ask is how can you use this rare data? And one way that people do it is to fine-tune and keep it at the end. So one hypothetical is that if you took all of your instruction tuning data and you just uniformly mix it into pre-training, you don't get a model that's very good at instruction following. So the takeaway is that how you order your data really does affect the downstream the capabilities of your model on these downstream tasks. And it's especially useful when the amount of data that you have is very limited. If you had like 50% of your pre-training data as instruction following, you do probably get a good instruction following model. The key challenge over here is that like a very small portion of it is actually relevant to the task that you care about.
So one question is that a constraint that every data should be seen just once, or like is it like you can either see it in the common mix or at the end, or like can you do it both? Can you do both?
Yeah, so you can see it at the start, you can see it at the end, but at the end, yeah, actually we'll get to this. Yeah. You want to use your rare data as much as you can. Maybe seeing it once is not using it as much as you can. You can get a lot more value out of seeing it multiple times. So I guess the data order is like used on like a lot of different algorithms today, like SFT, continual pre-training, mid-training. Like people use data order a lot. And then the simple question is, what is the best way to order your data if you care about this performance on your downstream task? So unfortunately, like answering this question, answering this question is very important. So I mean, like it'll tell you how to properly fine-tune, it'll tell you how to properly mid-train, and it'll also tell you how to properly pre-train in service of like your rare tasks. But unfortunately, something that Pratish also alluded to is that this question is on how to order your data is deeply tied with like many problem parameters. So for example, the domains that you are pre-training on versus fine-tuning on do end up impacting this. Also, like your learning rate schedule and how you like to like play with your optimizer end up impacting how you can use this rare data. The other thing is there's like repetition count, which is that you kind of want to repeat this rare data many times. And there's also like the optimal data order probably depends on scale of like models and also how large your pre-training and fine-tuning are. Basically, there's a lot of different complicated things in terms of all of these things are important for maximally leveraging your rare data and also confound you with what's the correct data order. So the goal of this talk is going to be able to build like a very simple framework that's able to take all of these factors into account. Like we kind of want to build a framework where we can search over the full space of design decisions and find the truly optimal data order in relation to all of the other design decisions that you can make during language model training. So that's the ambitious goal. We'll see how far we get to that goal. So in answering this question about what the optimal data order is, we have to make a couple of problem reductions to simplify the problem and make sure that we can actually like get a handle on it. So there's going to be a couple of reductions that we make that hopefully are still faithful to the problem setting, but make the science a little bit easier. The first simplification is that we're going to assume that we only have two domains. So in this talk, these two domains are going to be, one is going to be like internet web text, like so the C4, and the other domains are going to be representing some rare tasks that you care about. So like coding, math, or instruction following. We're going to be using star coder, find math, or Swan, and we're going to have like a limited number of tokens from each of these domains. And we're only really going to care about the ordering of the domain with respect to each other. So for internet text, throughout all of my data orders, the internet documents will be seen in the exact same order, and the same is true for the rare data. The only way that we change them is how we interleave the two domains with each other. The next thing is that in terms of the actual readout metric that we're going to want to look at, since it's easier, since like things scale more nicely and readouts are a lot more clean, we're going to look at validation loss. But we're only going to care about validation loss on the task-specific data. So, for example, if we're using star coder as the rare domain, we'll have a held out val set of star coder data, and we're only going to care about val loss on this domain. Basically, the only reason we would ever pre-train in this world is if it boosts our star coder val loss. We don't really care about whether you're good at general internet modeling. So, and then the next thing is we're going to talk about how we're going to measure this. So, in the spirit of this like data constrained world, we're going to measure data efficiency. So the quantity that we're specifically going to care about is for a given strategy. We want to measure its data efficiency improvement over a baseline. So how this goes is that we first fit a scaling law for if I had X amount of data, what val loss am I going to get? And then for a given strategy, we can measure the effective data of this strategy. We can see how much data does it look like this is training on, and then we can measure the data efficiency improvement. So more concretely, what we'll first do is we'll take some standard training algorithm and we'll fit some scaling law to it. And basically, this standard training algorithm will vary the amount of rare data that it gets access to. Then what we can do is that for any two given strategies, let's say strategy 1 got 3.2 loss and strategy 2 got 2.8 loss. What we can do is we can say getting 3.2 loss looks like the reference strategy with X amount of data. Getting 2.8 loss looks like the reference strategy with Y amount of data. And the data efficiency improvement, the quantity that we care about, is how much more effective data are you getting. So we take how much data both stars were trained on, and we take their ratio.
And you assume that you don't repeat the data, right?
So for the reference strategy can repeat or not repeat the data. So maybe this one actually does repeat the data. So maybe like each point over here looks like taking all of this data and doing 32 deblogs over it.
So do you think that that's the axis here?
That's a third axis here. So I think the reference strategy like gets better or worse based on how you repeat the data. But for what we actually care about, which is just a relative improvement, it's okay if the reference strategy is bad or good. We just care about like relative. We want to just put all of these things on a similar axis. We can like compare across strategies.
Sure, so can you explain the star? I'm a little confused. What the star and dot mean?
Yeah,
Star is
sure.
like your change.
So let's say I have like two training strategies that get 3.2 loss and 2.8 loss. That's completely independent of like how you trained it or whatever. You just get two models that have these losses. This star represents if I wanted the reference strategy to get 3.2 loss, how much data would I have?
So by reference, you mean like started
Yeah, some
This is
standard training
general.
algorithm. Yeah, this is like some standard algorithm, like some standard fine tuning algorithm. Yeah. The reference strategy is not important. The main thing is that you just want to compare, like, if I take two strategies and take their ratio, like, this is like training on effectively 2x
Oh, I
more
see
data.
what you're saying.
Yeah.
You're just like comparing like how good is this one as
How
compared to any
good?
reference.
It's just comparing two strategies.
But
Yeah.
Yeah, but like I still think in the x-axis, like even like the final point, the reference method or the you call it the standard method, I think it should be a single echo, because if you start repeating the data, that like a second like term in the equation that we also have to consider.
Yes.
But maybe it's hard to do it. It depends on how much, for example, fine mass, I think it's 12 billion or something like that.
Mhm.
I don't know how much we train for.
I think that makes sense. I do think that different training strategies would give you different references, and the data efficiency improvements would look different based on the different reference lines. But I think I will keep going because I don't think this will end up being really important.
Yeah.
So this is just like the measurement criterion at the end of the day. Yeah. So most of these experiments will be done in some very like standard settings. So we'll just take some 150 million parameter llama style model. And the total amount of training that we're going to do is for 4 billion total tokens. So this is like, I don't know, roughly chinchilla. And we're also going to have some rare token budget. So you'll be given like 4 million raw rare tokens. And you can do whatever you want with these rare tokens, but that's all you're given. You don't get any more. And you want to train on these rare tokens as best as possible. And then there's like other standard training details which don't end up being important. So now we can talk about like the baseline, which is standard fine tuning. So standard fine tuning looks like you first pre-train on some like common data. So you pre-train on your C4, and then you fine tune on your task specific data. If you have T total train steps, maybe you'll take like some small fraction of steps on the rare data.
So can I ask one question from the last slide?
Mhm.
Context window 4K and batch size 1. How many steps is this?
Yeah, it's the 1,000 training steps.
Oh, okay.
It's a small.
That's a very small number of steps. Okay.
Yes.
Okay. Sorry.
Yes.
Continue.
Yes. We can talk about when it becomes relevant later.
Okay.
So the first thing we care about is we're just gonna like really optimize the standard fine-tuning baseline and see what's the max performance we can squeeze out in the standard paradigm. So there's a couple of different things we can do. So the first thing is for learning rate schedule. We're not going to tune this just yet. We're going to fix it to standard fine-tuning practice. So maybe we'll do like a cosine learning rate schedule for pre-training, a cosine schedule, like learning rate schedule for fine-tuning, and also do an optimizer state reset when you switch from pre-training to fine-tuning, just like how fine-tuning would operate in practice. We're also going to tune the pre-training learning rate and fine-tuning learning rate, not that important. One important thing is that we're going to tune the repetition count. So what we do is that we want to get the maximal value out of this rare data. So we want to repeat it as many times as we can. So we can repeat it up to like some large number of times, like 64 times. But after that, you're going to start overfitting, which I mean, kind of makes sense that after seeing that so many more times, you're just going to start increasing your val loss on the rare domain. One important thing is that like maybe this is not like shown by like a lot of like these like scaling laws for repetition count, like the original paper and stuff. Their scaling law doesn't actually account for the fact that you're going to start overfitting. It's important to know that for our setting, there is some maximal repetition count that you just can't go past. So we're going to stick in that repetition count regime. So this is the optimally tuned fine-tuning baseline. But the fine-tuning baseline, or the data order for the fine-tuning baseline, makes two key assumptions. The first assumption that it makes is you do not need to see the, I think I flipped these.
Yeah. So I wanted to ask you also, so so since you don't see the rare data during your statement, is it rare data or OOD data?
I think OOD data is a fair characterization as well.
Okay, do you think we can change this assumption? Or like, what if we change it? What if we assume that the rare data will be, maybe this is a question for the
Perfect. This is a question at the top. We're going to break these assumptions.
Yeah.
So yeah, that's good that you're interested in this question. So I think I might have switched the names here, but basically like the first assumption is you do not need to see the common data during stage 2. So no web data while you're actually training on the fine-tuning data. And the second assumption is you do not need to see rare data during stage 1. Basically like fine-tuning, usually you're not allowed to actually change pre-training by like moving some of your rare data into pre-training. So the question that we're going to ask is like, are these assumptions like really correct? How much performance gains do you get from violating these assumptions? So the first thing that we're going to do is that we're going to challenge assumption 1, that you do not need to see any of the pre-training data while fine-tuning. So there's a very simple way to do this. What we're going to do is we're going to introduce a replay ratio. And what that means is that we're going to see some pre-training data during stage, instead of seeing it in stage 1, we'll move it to stage 2. So this is roughly what we're going to do. Standard fine-tuning looks like all web and then all fine-tuning. Now what we're going to do is we're going to do mostly web, like most of the web, and then we're going to do a mixture between the web and the rare data. And for learning rate schedule, we're also just going to like move it. Basically, we're going to control for the total number of steps whenever we make these changes, and the learning rate schedule changes accordingly. But this is just like a very controlled setting to see how much it helps to see the web data during fine-tuning. One pretty surprising result, at least to me, is that seeing this web data during fine-tuning is pretty helpful, even if you only care about performance on the rare tasks. So for StarCoder, FineMath, and Flan, what we do over here is on the x-axis, we vary the replay ratio. So high replay ratio means a high amount of web data, and 0 replay ratio corresponds to standard fine-tuning. And as you increase the replay ratio, there's usually some sweet spot where you actually get a better validation loss, even if you only care about the rare data.
Wait, for these results, was it that you're measuring after the same number of epochs in terms of like the rare data, or was this like the number of epochs of the entire like the number of training steps? Are you fixing the number of training steps?
So the number of training steps are going to be fixed to like the 4B total tokens that we're going to do. And the other thing that we did for repetition count is we tuned the repetition count for 0 replay ratio. So we tuned the repetition count for standard fine-tuning for all 3 of these. And then we fixed that repetition count whenever we change the data order.
Can I ask a question? For each of these replay factions where you change the percentage of the data, did you also tune the learning rate for each one?
So we tuned the learning rate for the baseline.
Okay, but not for each data.
Not for each data mixture, but I mean, like offhand, I can tell you it doesn't matter too much.
Okay.
The optimal learning rate doesn't change.
Because you tuned it, or you just don't, you think?
Or like I launched a couple runs.
Okay.
With different learning rates and only one of them. Yeah. So yeah.
Oh, sorry. Oh, can you go back to the slide? So the reason I was confused is because so I thought you were this one looks longer, so we were confused like whether you're doing more steps.
So the total number of steps during training is fixed. The total number of blue steps and the total number of pink steps is fixed. But if you add a replay ratio, your fine-tuning stage becomes a little longer.
Okay.
And correspondingly, your pre-training stage becomes a little shorter.
Okay. Oh, I see. Okay.
Does that make sense?
Yes.
But in your case, since FT data is so small, it will almost not change anything.
So the fine-tuning data is like 4 million tokens, so 0.1% of training. And then we're doing it for 64 epochs, so it's like 6% of training. Yeah.
So when you say replay, if you're removing data from stage 1,
Mhm.
is it actually being replayed, or you're actually using less purple data, less unique purple data?
Oh, sorry. I think replay is a misnomer here. I'm not actually like repeating data points. So I guess like one of the assumptions for this is that like pre-training data is like infinite, roughly.
Okay.
So we never repeat pre-training data. Yeah. So yeah, I guess replay is maybe not the perfect word for it, because usually that implies repeating.
You're increasing the number of steps that you see this data as well, right?
Increasing the number of steps you see the rare data.
Yeah,
Yeah, that's
because you cool down earlier and then you warm back up, and so like the starting number of like amortized flops in the models change as you change this ratio too.
Okay.
Yes. You do extra steps on the fine-tuning, like fine-tuning.
But it's the same flops though, right?
It's the same
Remove
flops.
For the total budget,
Yes.
right?
So you always see 4 million tokens from the rare data.
4 million times 64. Yeah. So 4 million tokens for 64 repetitions.
Okay. So when you replay, you don't reduce the amount of rare data you see.
You do not reduce it. It's the exact same repetition count and exact same budget.
You just shift to the left and you start the step 2 earlier.
Yes. Yeah. Any more questions about the setup? Yeah. So
I have a question. Okay. Sorry.
yeah, no, of course.
What if we change this from stage 1 to stage 2 to only one stage?
Mhm.
and you fix the learner rate to be like the same as scheduler, which means you don't anneal and then you reset, so that there is no annealing. You get like one step and you do the switch in the data loader scheduler at the end of training. Do you
You're
think-
predicting my talk perfectly. This will be the next step. So this is if you're only allowed to change the fine tuning stage. Yeah. So this is only if you're only allowed to change the fine tuning stage, and you get these like data efficiency gains. So for flan, for example, you're getting like a 1.9x data efficiency gain. And what that corresponds to is that like you're somehow like able to train on effectively 2x more flan data, which I think is like a pretty cool boost that you get on your rare data.
So the key thing here is that by replaying, you allow rare data to be seen more. Like so is it like it prevents overfitting? Like is that a way to say that why you get this ability to see more?
I think so I don't have like the full explanation, but like maybe the rough intuition is that you're overfitting less on the rare data, and by doing this like joint training, you're able to train on it without overfitting.
Is it more or longer?
You can train for you can see more epochs and then you overfit.
No, but the number of epochs is same for everything.
It's longer.
Longer.
Yeah. So I think this is like I don't have the full understanding. I have some hypotheses, and if we have time, we can go.
But like you have 64 epochs, right? So if you do not replay, you overfit earlier, like a 32 epoch or something like that. But if you have replay, then you overfit later.
No, so the 64 epochs, right, was set with the no replay. This is like the best loss you can get without overfitting with no replay.
Okay.
Yeah. Makes sense?
Yes.
Yeah. So there might be an additional benefit that you can repeat the data more, but I don't think I've seen this yet.
Right. So you can potentially do 256 when you're
Maybe,
doing replay.
But I don't think I've seen this experiment.
So we did a bunch of CPT experiments and we found that like for different durations, you can actually find different like optimal learning rates that prevent overfitting.
I see.
So you may need to tune that also.
Maybe
for
the
duration.
learning rate might, I haven't tuned it very aggressively
Yeah.
for the replay fractions, it might change. Yeah, so yeah, I think like the main thing is that like usually in like catastrophic forgetting type literature or like continual learning, replay is used to like prevent forgetting the old task. And I think the kind of, I don't know, this qualitatively different thing that's going on over here is that it's helping you learn the new task even better, which I think is pretty cool. So this was talking about this like first assumption that you do not need to see common data during stage 2. We kind of show that this assumption is wrong and that you can get better fine-tuning performance. The second thing is like, what if now?
I had a question, like, so what's your hypothesis on like why this works? Because I guess we're not seeing it in more steps, and we're not sure if it's reducing overfitting because 64 was set with like to avoid overfitting.
Mhm.
So what I guess is the intuition and like why it improves performance on the rare task?
Yeah. Yeah, I think I have like a couple of like a little bit of speculation about this. So one thing is about this like small step count thing. Actually, I think I have that. So the first thing, which is like I don't know if you guys have seen before, but if you like fine tune and like with like a small amount of steps, there's like a loss in stability at the very start, which is that you see this like loss spike, and then most of fine tuning like it eventually goes away. And this loss spike is usually benign in that if you train for like enough steps, it goes away. One possible hypothesis, which I'm not like fully sure about, is that maybe you're just getting to like train for like more steps, right? So you get to like squash this like loss spike even further. But I don't think this hypothesis is fully faithful because even if you don't see a loss spike, this sort of replay benefit still helps. So I don't know about that. And then the second thing is that like, and I think there's like a tendency for you to be able to like overfit on like finite samples. And replaying somehow like does this. I think I probably don't want to get into this too much right now. Maybe we can get into it later. I think it's more interesting to see the mid-training experiments, and we can like come back here. Because to be honest, I don't have a very good answer as well. Yeah. So the next thing that we're going to do is that now, what if you're allowed to actually change pre-training fully? So you can change the data mixture during pre-training and actually introduce some rare data over there. Does this help your data efficiency? How much additional gains can you get from this? So now, I mean, as you mentioned, if you're allowed to change pre-training and fine-tuning both jointly, there's no reason to have them as separate phases. You should merge them all into a single stage. So what we do is that we have a learning rate schedule that's joint across stages now, and we try to find the best pre-training data order, learning rate schedule, learning rate, etc. One important thing is that your learning rate schedule is actually very critical to this process. for example, one thing that you might expect is that you might just like slap on a normal cosine learning rate decay, cosine like a learning rate schedule. The issue with this is that like sometimes it's actually harmful to put all of your rare data at the end of training with a cosine learning rate schedule, just because like the area under the curve of like a cosine learning rate schedule is like very small at the end. Like there's very little like actual like, I don't know, mass under that curve, so you're taking like smaller steps and whatnot. So sometimes if you don't use the right learning rate schedule, it can actually hurt you to do like the fine-tuning data order. So we need to be like pretty careful about this. What we're gonna do is that we're going to use the WSD learning rate schedule. So this corresponds to like warm up, stable, decay. What that means is that for the first part of training, we'll like rapidly warm up our learning rate to like some peak learning rate. Then we'll be stable for most of that period. And then we're gonna decay very aggressively. So this is what the learning rate schedule looks like. One really interesting consequence of this learning rate schedule is that the training proceeds in a different manner. Usually for cosine learning rate, you're like smoothly decrease your loss, and then maybe at the end you like slow down your improvement. For WSC, it's the opposite. You're slow at the start of training, and at the end of training, you like rapidly improve your performance. So this kind of indicates that a lot of the learning is happening like at the end of training, or at least like the loss decrease is happening at the end of training. And for WSD style data orders, where you like anneal very sharply, it's now a good idea to put your rare data towards the end. This is not a new observation. This was observed by many CPM. It's a really good paper. But I think that this is really important detail to nail correctly to actually get data orders to help your performance out. So for example, in our case, what we can do is we can tune the cooldown duration. So what fraction of the training run should you sharply decay your learning rate for? What we find is that there is some like correct cooldown duration, and it ends up being like a very short amount of training, like something like 5 or 10% of training should be spent cooling down the learning rate. And like maybe something like a long cooldown duration corresponds to doing like a cosine learning rate schedule. So it's like a pretty bad idea to use cosine learning rate schedules instead of cooling down very aggressively. And so now we have like a new baseline. Instead of fine-tuning with 2 separate learning rate schedule stages, we have the WSD baseline, which basically does everything in one. Like it's still going to be all pre-training data followed by all fine-tuning data, but at least a joint learning rate schedule. And this gives huge data efficiency gains. Like this is not even like a big focus of this project, but just like you can get like for StarCoder, for example, just like merging the learning rate schedules can give you like 10x data efficiency gains, which is like a huge deal to be able to like merge this training.
I have a question, but I'm afraid it might be in the next slide.
This is the next slide.
This is the next slide. Does this answer your question, or is it a different question? So
Actually, if you go back to the previous slide,
Yeah.
So like, do you think it's because you get the benefits of WSD, but also do not get the benefits of loss spike, or are there other reasons why you think the joint learning?
Oh, I think
This was my
the
question, by the way.
Hmm?
This was my
oh,
question.
this was your question. Okay, yeah. I think the joint learning rate schedule helps because of 2 reasons. I haven't avoided on the reasons. One is that like cooling down and warming up is like not a good thing to do in general. That's not a fun thing to do. And the second thing is that the optimizer state, you have to reset it when you do fine tuning, right? Like you lose like the atom like grads or whatever, and when you do a joint thing, you don't lose that.
Okay.
But I haven't avoided on which one is.
So also, do you think if you warm up, sorry, not if you anneal the model to 0 learning rate and you start now to fine tuning, do you think now you would need to have a longer SFT step or some maybe a longer step 2 training to be equivalent to that one without any annealing? Because like is it true that like just like after you anneal the model becomes, for example, like harder to start the fine tuning again, or like
Yeah, I think that's
What if we
true.
get,
I think
like-
if you bring the learning rate to 0, it's annoying to start fine tuning, and you might have to do more steps or something.
So yeah, so do you think it would be possible to mine the same performance with just like extend the training, step 2 in this case?
How would you extend the training of step 2 with like limited data?
I mean, assuming that you have more. Yeah.
I mean, I think the key assumption here is
Yeah,
that
the key assumption is that.
you have a limited amount of rare data. And that's why replay is necessary to drag up that training.
Now here, you're not coupling the data mix to the decay, right? The data mix actually hits towards the end of the decay still, given the small amount of?
Yes, so I fixed the data schedule and I'm only tuning the learning rate cooldown period right now.
And the data schedule is such that the fine tuning is less than 5% of the total time, right?
Yes,
So we're still in a domain where, a regime where the decay happens before. the data
Yes.
decay.
and I think in other experiments, I found that these quantities are not like intrinsically tied together. Like sometimes you start the fine tuning data mix before the cooldown and sometimes it's the other way around. So now what we're kind of interested in is searching over the full space of data schedules, where there's two things that you might want to do. One is that you might want to replay pre-training data while you're actually fine-tuning on the rare data. So this is bringing common data into stage 2. And the second thing that you might want to do is allocate some fraction of your rare steps, move some fraction of your rare steps into stage 1 rather than stage 2. We're gonna basically only consider these 2-stage data schedules, and we're gonna parameterize them with 2 free parameters. The replay ratio controls how much common data is in stage 2. And the stage 2 allocation parameter alpha controls how much of your rare steps do you keep to stage 2. So for example, under these assumptions that we talked about, the assumption that you do not need pre-training data while fine-tuning corresponds to a 0 replay ratio. And the second assumption that we talked about, which is that you do not need rare data early, corresponds to assigning all of your rare steps to stage 2 rather than stage 1. One important thing that I want to mention over here is that when we add rare data to stage 1, we're taking it out of stage 2. And this is necessary because if you do not, then you're going to repeat the data way too many times and you're going to start overfitting on that data. You need to control for this like total step count.
Are you doing a warm up for stage 2?
Warm up. So this is all one learning rate schedule.
I see, so like it's stable, like you keep it stable learning rate in between stage 1 and stage 2.
Yeah, so basically like the decay parameter would control whether the learning rate decay starts at stage 1 or starts at stage 2.
Mhm.
But I mean, that parameter is completely independently tuned of like the actual data order.
Okay. Then how do you mentioned the training loss spike
Mhm.
in between stage 1 and stage 2.
Yeah,
What do you do to remove it? What are you doing to remove it?
there's, I guess replay ratio is one thing that you can do, but there's nothing else really.
Okay.
that, is done.
So you're doing warm up stable decay and you're controlling the annealing, but like, did you actually try cosine schedules? They didn't work?
Yes.
Okay, interesting.
I mean, it depends. So to be clear, like cosine learning rate schedules, sometimes it's still beneficial to keep the rare data at the end, but you get even better performance from doing WSC.
Interesting.
So for example, this like 0.99 cooldown duration, right? This is like, I mean, this is like effectively a cosine.
Sure, yeah.
Or linear decay,
Linear decay, yeah. So I mean, it's not a cosine in that the shape is like linear, but it's still a cosine in terms of like you're decaying from training.
But wait, you're saying that this is interpolating between two schedules, like, this isn't actually a cosine decay schedule, right? This is just saying you're decaying, like you're doing essentially like a warm up and then a linear decay.
Yes.
Okay.
So the learning rate schedule, I guess, like would be like you warm up real quickly and then you like cool down slowly for all the training.
Yeah,
And a cosine learning rate schedule will look like you warm up quickly and then you cosine decay for all the training.
right.
Yeah.
But the
the shape
reason
of it.
you're comparing the 0.99, right, is because you're just saying that the lane rate is very low at the end when you have that, like you don't have any high linear rate part of the replay.
But did you
Yes.
try keeping like actually doing a learning, like a cosine decay and then changing like the phase 2 to start at the same thing you found to be optimal as the like your optimal, like at the last 5% or something?
I see. So you're saying like make the first phase cosine instead of stable?
I mean, you just have one cosine decay schedule and
Okay, so one cosine learning rate schedule.
right, and then just like change the duration, the duration where you're doing the like data mix phase 2.
Yes. I have done this.
Okay.
And what that says is that you still want to keep the rare data towards the end.
Yeah.
Like it's better to
yeah,
move
of
the rare
course.
data to the end.
Right.
But it also underperforms doing that same data order with WSD.
Okay, interesting.
Does that make sense?
Yeah.
Yeah. Cool. So
This one is joint learning rate, right?
this is all joint learning rate.
Do you think the doc might change if you change it to
To what learning rate?
If you do a stack measurement, like 2 different areas, you anneal and then you warm up again.
Oh, yeah, so I think the results would kind of change, at least the replay results wouldn't change, because we did those experiments in the first, right?
But adding the red.
Oh, adding the rare data to the end, I haven't done those experiments yet, I'm not sure how it would change. I think it would be relatively similar, but I'm not sure. I think it would be like all relatively similar, but all the losses would just be uniformly worse.
Because I don't know if the result will be the same or not, because if you anneal and then warm up, that means in the left, the standard one, you start warming up on like purely new data, right? It's OD data in this case also. But for that one, it's a new, or it's not a new data, it's a rare data, but it's not an OD data, right?
Yes.
So I feel like there's.
Yeah, I think there would be a difference. I think we'd have to run the experiments to see. Yeah. But I do think in the case where you were allowed to change the pre-training, maybe it is realistic that you're able to like merge the learning rate schedules. And it does seem to be the case that merging the learning rate schedules is usually better. So yeah.
So for your schedule, like the decay schedule, is it like you get the best performance when you still have like stable portion of WSD still present? Like is that like
that doesn't end up being fundamental. Like sometimes it is, sometimes
it's not necessary that
it's not
decay
necessary.
starts. Because you had this curve where if it's completely decaying in the earlier thing, then it's not, it's suboptimal, right? So I thought that maybe the benefit is coming because the rate is high.
Yeah, but I think like when you tune this parameter, sometimes it ends up being longer than the stage 2, and sometimes it ends up being shorter than the stage 2. So it's hard to say whether like So I guess like in this data schedule framework, we can now control the replay ratio, and we can control how much data is in stage 2, and roughly we just sweep over these parameters. So the stage 2 allocation is alpha. 1.0 corresponds to everything in stage 2. And replay ratio 0 corresponds to no web data. So 3.27 over here would correspond to the WSD baseline. These top right corners are always the WSD baseline. And now there are things that you can do, such as vary the replay ratio or introduce data into stage 1. This plot is kind of dense and we can return to it. I just want to like make some important observations on this plot, and then maybe we can look through the full set of numbers. One thing that we find is that the replay is most helpful when the data is unseen during pre-training. So for example, if none of the rare data is in stage 1 and all of it is in stage 2, we get this blue line. And here, tuning the replay ratio ends up being like a really essential quantity. But if you have some amount of, like in this case, like 75% of the rare data, if you keep it at the start of training, or like in stage 1, then you don't actually need the replay ratio anymore, or it's like the model performance is a lot less sensitive to it. So the model performance, like replay helps more when the data is like more rare relative to the pre-training, like when it's less represented by the pre-training data. It's one thing that I want to bring your attention to. Another thing that I want to bring the attention to is that we can measure the data efficiency gains, where we're only allowed to change row, or only allowed to change the replay ratio, or you're allowed to change both row and alpha. If you're not allowed to change either of them, we're going to set this to 1x data efficiency. And now if you can only vary the replay, you can get like some like 1.5 or 2x data efficiency. And if you're allowed to also change pre-training, then you get like even higher data efficiency numbers. One interesting thing that I want to draw to you over here is that like star coder, being able to change the full data schedule is not that helpful. Only changing the replay ratio is actually enough to get the full performance gains for star coder. So this shows that you don't actually need to change pre-training for sufficiently rare data. But maybe for other domains, it's actually kind of important to like but you can still get like, I don't know, 50% or 70% of the gains by keeping all of your data, like or like 40% or 70% of your gains by keeping this rare, by only changing the replay ratio and not doing anything else.
So what do you think makes it different for domains? Like, is it like you're going farther from pre-training mix?
Yeah.
That the ratios keep increasing? Is that like a reasonable hypothesis here? Like the more different the domain is?
Yeah, I'll preface this with I don't have a full understanding to this question. I think it's a really important question about like what domains can you get away with only replay versus not. But some things that I can say is that star coder, one interesting thing about C4 is that it's explicitly filtered for code. So there's no code in it. Fine math is like kind of medium, and then flan is like probably the most in distribution. So in this like
It just happens.
okay. In this arrangement, star coder like is the most OOD, and maybe there, it happens to be that replay is enough. I don't have a good understanding. There's another thing, which is that these rare domains, if you pump up like a lot more data for them, so the amount of rare data you get access to is like a lot more, then a replay is not enough. You do need to change the full schedule. But if the data is rare, then you don't need to. So there is this general thing that the more rare the data is, the more that replay is sufficient. Yeah, Christina?
Oh, no, I
Okay. Cool. And one final thing that I want to talk about is this like model scale, which is that one concern you might have is that all of these are true for 150M models. Here, what we do is we just take one slice of the grid and we only tune the replay ratio and we slowly increase the model size. What we find is that the actual replay ratio, it changes a little bit, but it's honestly relatively consistent and the actual trends seem pretty similar. And at least as you increase model scale, you still need this replay ratio. You can't get away without doing the replay ratio. So yeah, but I think like there's like this gives you like a bit more fine-grained insight into how replay can continue to help your performance and how changing the pre-training can give you further performance gains. And it also we also give now a quantitative way to measure how much do you get from changing pre-training versus how much do you get away with, like how much can you get away with only changing fine-tuning and doing it like truly properly.
Wait, can you go to that actual number of grids again?
Yeah.
Is it fairly consistent across domain, or do you find that this tune is very different? I kind of look at your x-axis. So these are all the same. Like generally the stage 2 allocation. Oh no, the stage 2 allocation does change substantially.
Yeah, so the purple boxes correspond to like the optimal schedule. The replay ratios end up being like relatively consistent. The stage 2 allocation ends up being pretty different. This is yeah, stage 2 allocation seems like a lot more domain dependent.
So it varies all the way from like a quarter to 100%.
Yeah.
Is it known like some degree of like similarity or overlap between these data sets and C4?
Yeah, I think the best thing is like StarCoder has like C4 has filtered out curly braces.
Okay.
So I think like StarCoder is like really no overlap versus like Flan is like instruction following and more likely to have overlap.
One thing that I wonder is like, is that like, okay, so we do consider that you have alpha and 1 minus alpha, but like, I feel like when you're seeing it during pre-training, because there's so much of the data, maybe you can see more of it. Like, do you think that fixed epoch count constraint is like probably not telling us the whole story here? Like, if I could, like, what if I could like do 10x alpha during pre-training? I feel like, and then still 1 minus alpha at the end.
Yeah.
Would that be too overfitting? I feel maybe or maybe not.
So that would be another nice thing if like alpha, like putting a low alpha allows you to repeat the data more.
Yeah.
And I've done very small number of experiments here, not rigorously, but I don't think it changes the optimal repetition count that much. But I only tune like 2 to the n repetition count. So for example, like all of these are done with 32 repetition count. I don't think you can get away with 64 repetition count if you change the alpha.
But the 64 doesn't sound like a very high number.
It's a very high number. So I think like if you think about these like standard repetition scaling laws, like something like 4x is like the correct number. They're talking about the marginal returns on the data. So like after 4x, it's just not worth your compute that much. Here we've fully abandoned compute. I don't care about compute. I just want to like repeat the data as many times as I can. And in that world, you actually can repeat the data like many more times before you actually start like literally overfitting the data.
I'm curious about this, right? Because like, I mean, let's leave like the math and Flan alone because they're slightly different. But like StarCoder, you're looking at validation loss, but you're not actually looking to see if the model can program. And like, I'm curious to see, do you think that it would hold? Like, I don't know if 100 million parameter model can actually do val, but do you think that like that doing 64 epochs like actually improves its downstream task performance, or is this like, or does it need to be like studied whether these still correlate when you do that many epochs? Like, I'm not sure that those things will be the same.
I think this needs to be studied.
Yeah.
I don't have I think yeah, val loss might be a little too in domain. Like there's like a distribution shift when you're doing a val benchmark, and then you have to like account for that. Yeah.
Okay.
I think that would change it a little bit, but maybe in the interest of answering that, there's like some like quick implications. So you can start measuring this for maybe like more real scale things rather than just like toy science setup. So one thing is that like I mean, I can't actually change the pre-training of like an 8. Okay, whatever. I can't do pre-training an 8B model, so I'm gonna like take fine tuning and I'm gonna replay, like at least I can test my replay conclusion. Like, does it help you to replay pre-training data while fine tuning on rare domains? So we take 2 like pretty rare domains. So one example is like web agent fine tuning. You'd imagine that Llama 8B instruct has not seen many examples of like web trajectories that you need to like do these agent tasks. What we find is that when we fine tune with 0 replay ratio, you get some performance.
How do you know? How do you know?
I have no clue. This is my guess.
Can we tell it within the val loss?
Yeah, that's a good idea actually. Maybe you can use val loss to audit it. Yeah. But one thing that we can do is that you can take this like agent instruction tuning data. All we do is we just mix in Open Hermes or UltraChat or something like this, and you actually get much higher performance on this like agent, like web agent task just by mixing in instruction following data. And sometimes these gains can also be higher than literally mixing in like extra agent data. Like mine to web is like a different agent task, and it's literally more helpful than doing that sometimes.
Okay, is this like a way to tell like what the model actually trained on?
This might be a way to like audit like is the model good at
Benefit by replaying that?
Wait, hold on. Some of these data sets are like GPT-4 distilled.
Yeah.
That's higher quality than Llama 8's instruct data. Like,
Yeah.
it is actually not surprising at all that training on the Open Hermes should improve you, because like GPT-4 is better than Llama 8.
That's fair
Right?
enough. So I'll give a second demonstration.
Okay.
The second demonstration is that there's like a low resource language like Basque,
Uh,
and you want to like get performance on this. So we're gonna measure like COPA, which is like some like natural language understanding benchmark, but translate it to Basque. We'll measure like accuracy on this benchmark. And what we're gonna do is we're gonna replay this training corpus with Slim Pajama, which is like presumably like a good approximation of what Llama 8B was trained on in the first place. And when you replay this data, you actually get better performance on this Basque benchmark. You also see this improvement in val loss.
0.8, like almost 80% of the data is RPG.
Yeah. And that's the correct trading mix to get the best Basque performance.
And
And
here,
this is
presumably you've trained as, like you've exhaustively seen how many times you can repeat this data, and then you've also like changed the replay fraction here.
I think the
Because I see fraction, but I don't see like duration or like how this impacts this.
So I think this plot over here might not have the optimal epoch count on Basque, but you still see this trend when you do the optimal epoch count. And we've also scaled the total amount of Basque tokens. So as you increase the amount of Basque tokens, you still see this like gain.
But this is a fixed epoch count of.
Yeah, this is a
Basque
fixed
data
epoch
is-
of Basque.
So when you go up to 80% replay, you're also
You're
dramatically
increasing the
increasing
training.
your
The number of
flop
training steps is 5.
So these are not flop equivalent.
These are not flop
But
equivalent.
you chose the optimal epochs based on the standard right tuning.
Uh,
So that
yes.
one's optimized, like you can't, like if you trained for even longer.
It wouldn't help.
It wouldn't help.
So like that is the best you can do without replay.
Yeah, I see.
So that's why like I see replay as like, regardless of the reason, it seems to be some fundamental object that allows you to like get more performance out of your rare data.
I think one thing that would be really cool in this graph is you can also like we plot the loss spike magnitude
Oh
over
yeah,
there,
yeah.
like maybe on the second y-axis, and
Uh,
see like I would love to see like is the loss spike increasing with replay and like the duration of the width of the loss spike also.
yeah.
And that would inform a lot.
That's I can do that. The duration of the loss spike is similar for regardless of how long you train. And then it's just like how, the magnitude, I don't remember off the top of my head.
Also, like if maybe the magnitude is correlated with the fraction, then maybe that also explains.
That also helps, yeah. Cool. Another thing, this is more of shout outs, but like, so I don't know if you guys saw Marin 8B, which is like a language model that we trained on like the Stanford Compute. What we used a lot of these lessons about how to optimally mid-train when doing Marin 8B. So that's what informed this, like, I guess, jellyfish and starling is what we called them, but these cooldowns. So we did have replay ratio, we did have like a sharp WSD, like learning rate cooldown and stuff like this. This is all standardly known in the literature, but we tuned some things to make it work for us.
Oh, it's finished training or it's training?
It's finished training, or like we released it. It beats Llama 8B on like 75% of the benchmarks.
Oh, wow.
So I think it's a good model. Yeah. But I think like there's still a lot of work to do for like SFT and RL. Like it's a good pre-trained model, but not a good like SFT or RL model either. Yeah. So yeah, all my experiments, you can find them on the Marin thing. It's a really cool project. We've open sourced literally all the experiment ideas, all the weights and bias runs, all the code. You guys should check it out. Yeah. So it's cool.
Also mid checkpoints.
Oh, we all the checkpoints as well.
Any link from a checkpoint.
Yeah, so everything's on Hugging Face and their code base and everything like that. So it's a pretty nice initiative, I think. The other thing is that there's like some implications for pre-training, which I guess are not fully answered by this work yet. But when can you get away with fine tuning? There are at least some domains where you can actually just purely get away with fine tuning, and you do not need to change the pre-training to get the maximal value out of your rare data. Cool. Yeah. Any questions?
When you go to take this from, we only care about star counter, star coder performance to we're training Marin, how do you adapt these ideas to that?
So I guess like when we were training Marin, like I don't know, we only care about MMLU. But that's a reductionist joke. I don't think that's actually true. But I do think that like we don't actually care that much about like your like C4 loss, to be honest. Like C4 loss is something that we like really aggressively tracked during the pre-training. But once we started mid-training, I guess we cared about it a little bit, but we also like took these more high quality domains and started measuring your val loss there. And we cared a lot more about that.
I normally just help with a bunch of different domains, right? It's got varying tasks. So like, did you split it apart? Did you have multiple different mixes, or did you just have like a rare data versus not? Like, did you have multiple rare data?
Yeah, so we use like Paloma. So I mean, like it's like I don't know, like Dolma has like a bunch of like rare domains that they've released, and we can like measure val loss on these domains. I think one thing that I was actually made me like pretty optimistic about this project is that a lot of the time we were optimizing against val loss for when we were like doing the pre-training and fine-tuning, and that didn't end up being like that bad of a decision. A lot of the interventions, we did very simple interventions, but for a lot of these interventions, the val loss did correlate with the downstream accuracy that we cared about. But I mean, it's val loss on like the right set. So for example, like really optimizing this rare domain loss doesn't make you a good instruction following model. But if you measure val loss on instruction following data, then it is fine to like go climb on this.
I think like something I that could be interesting is so something that's been reported in like what is this paper called? Do you know, have you read like the simple and scalable strategies to continually pre-train?
Oh yes.
Yeah, so they've also like mentioned the training loss spike, and that the validation loss also, there's like a spike in the validation loss that corresponds to the training loss spike. And I'm wondering like how much of these things like come from the unlearning that happens during this like spike. Like if you, for example, like can you get the same gains just by interpolating a with replay like only during warm up or something, and then like training with like 100% rare data like afterwards? Like I'm wondering like how much of the effect is coming from the training.
I think it's very possible. Like I think a lot of these results might be like spike mitigation, but one like experiment I'll share that like maybe says that spike is the wrong abstraction is that like there are times when you're doing this fine tuning where you do not see a spike and like the loss is just decreasing the entire time, and replay can still help in these regimes. So I think like the spike is like causally downstream of something else that's happening when you're changing the data distribution, and it's like important to like smoothly transition the data distribution. But I think like another thing that's like indicative of this is that like, for example, I think it was this plot that like you do not need the replay if the rare data was seen during pre-training, right? And then this gives credence to like you kind of just need a smooth handoff between pre-training and fine-tuning, either rare data in pre-training or common data in fine-tuning. So that's also like probably very realistically what's happening.
But what is an example where like you didn't see a loss spike and you still saw?
So for this VASC training, I saw
The
this.
back training, okay.
Yeah. So there's some VASC training that had like VASC training with low learning rate doesn't have a loss spike, but if I mix in data, I still get an improvement in the loss. Yeah. Yeah, cool. I'm gonna skip talking about the synthetic data stuff.
But like quickly, like what?
Okay, I can do a very quick. I don't know. I was worrying about the time.
Conclusion.
Oh, I'll give you the conclusion. Yeah, I'm gonna go to the conclusion. Maybe we can talk about the synthetic data stuff offline. Yeah. I think like my general thoughts on this is that like the question that I'm very excited about is how you can best leverage rare data. So I think most of language modeling has operated in this regime where like the real bottleneck was compute. You didn't have enough compute to do all of the training that you wanted to. And I think a lot of the research has ended up looking in like systems and things that make your training faster on like a per compute basis. One direction that I'm quite interested in is predicated by the following not too like crazy bets, which is that first, compute will continue to increase. Second, like there's not like the real data is not going to increase that quickly. Like if you measure the amount of pre-training data increasing or the amount of rare data, like the real, like I'm ignoring synthetic data here, just like the amount of real data is not going to increase that quickly. And the third thing is that our algorithms are not information theoretically optimal. So just because you did like the maximum repetition count doesn't mean that you extracted the maximum value from the data. So I think that you actually have to change your training algorithm to extract the maximum information value from this data. And so I think that my general goal or like problems that I'm interested in, and I'm sure you guys are interested in too, is designing these algorithms that can squeeze out as much information as possible from these data points, even if it costs like a lot more compute, even if you have to like, I don't know, spend 5x computed fine tuning to epoch or to like add replay ratio, that's like fine. Like how can you just get the truly information theoretically optimal like learning algorithm for like both rare domains and pre-training and such?
That sounds like a challenging research agenda to pursue in an academic environment.
So I think that maybe I actually have very strong opinions about this. I think all of my experiments, like most of my experiments here are on val loss. And I think val loss is a quantity that scales ridiculously nicely. And I think that I found that across, like I'm now doing like pre-training research, but my pre-training research is on 50 million tokens. But things just scale so nicely that you kind of can just do science at small scale, try to get some understanding of what algorithms are going to like extrapolate and do it there. But it also limits you in the type of algorithms that you can work on. If you're at 50 million tokens, no model is good enough at rephrasing, so you can't do like synthetic data type interventions, but you can still do like classical learning algorithm interventions, like all of these replay things. You don't like, you can just measure val loss. But I do think there's a lot of things that are challenging to do in an academic agenda, and maybe I can't do those.
Well, we do have internships, Bill.
Cool, yeah, that's all I have to say. Thank you. Yeah.
What's the TLDR for the synthetic data stuff? That was good.
Oh, yeah, sure. I can do the quick synthetic data stuff. So roughly you want to like blow up your effect, like another way to blow up your effective data count as like the quantity that we've been talking about is to generate like more rare data. And so there are like a couple ways to do this. There's like verifier based, which is like more like RLs type things where you have like the domain specific verifier, but I think that only works for like things like math or coding. There's distillation based synthetic data where you need a larger model, but that doesn't make you like, it's not necessarily going to help you make the next biggest model. It can, but it's like not obvious. And then the third type of thing, which is like a lot more scalable, is augmentation based synthetic data, which like has been like historically super useful. Like CPAR10, the only data efficiency gain that we've ever really got was to like Gaussian blur and rotate the images. So the question is like, does this work for language models? Which I think Pratish has done some very pioneering work on. So I think Rephrase the Web is a great example of how you can like...
You would have missed this wonderful picture.
Have you guys not seen this picture before?
Well, there's the hearts. The hearts would be important, right?
The hearts are mine. But
That's the original comment which I have put in.
yeah, but I think yeah, so this is like a great paper. I think that this is like the first time the data augmentation has really worked for language models, where you can just take this like data and like rephrase it and get like more effective data points and continue training. And I think this like perspective has also been pushed in this other work like from people in my lab, like NT-Graph. So what they did over here is that they have this setting where there's like a small number of books, like 1 million tokens, and you want to get really good performance on this. You can basically like, no matter how much you epoch the original data, no performance gains. But these rephrasing style or this NT-Graph style augmentation continue improving performance. One thing that I did was like a very simple experiment, which is that the generators in these things are usually like much larger than the like, or model that you're actually training. Like you're using ChatGPT to do the rephrasing to train like a small model. So you just take this like rephrasing recipe, and what you find is that you do not need a very strong generator to do this. Just like an 8B model is good enough to teach an 8B model. So for example, epoching over the data gets you like some 2% gains on this benchmark, but this point over here is like ridiculous. It's 1,000 rephrases of the original doc. Like each document is rephrased 1,000 times and you're just doing next token prediction on them. And you still continue to see log linear returns in your performance. which is kind of ridiculous. And there's no stronger generator or anything too. So maybe self-improvement is solved, you get exponential takeoff, AGI is here. But I think the issue is that rephrasing doesn't always work. So for some domains, it works. Some domains, even though the RAG performance gets you like a huge performance gain, the actual rephrasing augmentation doesn't do much better than training on the original data. So that's kind of sad.
I also suppose like there's the data set size. Well, no.
The data set sizes are similar. They're all like around 1 million, 2 million tokens. Yeah, I have some hypotheses for these we can discuss later. But some issues with rephrasing is that you can't really scale it. One thing is that if you make the generator better, like take the generator from an 8B model to like a 7dB model, you do not actually get that much better performance. Rephrasing is kind of like this simple task that even a small model can do. And if you keep making the model bigger or the generator model bigger, you're not actually getting that much more performance gains. And the second thing is that like your hope, like one hope is that you can do this multi-iteration. So you can like train on the rephrases and then make that model the rephraser, and then train on the rephrases and make that model the rephraser, and hope for like some exponential improvement. You don't get that in practice. So like training your model on the rephrases doesn't make you a better generator. So I think overall, my opinion is that data augmentation is really good and it's going to give you these like large performance gains. But the current data augmentation techniques that we have don't have like a true self-improvement operator to them, and that we kind of need to figure out something that can actually like allow you to pour even more compute into the process to generate even better data and to train better models. But yeah, those are my thoughts there. Any questions about that?
Have you tried going the other way? Like, what's the smallest you could make the model and get improvements?
Yeah, so if you take the 8B and the 7dB, so the 3B model over here is like markedly a little worse than the 8B and the 7dB, and I've done the 1B and it's just a flat line.
Okay.
So
and I'm curious, like, did you look at this and like is there any like clear like artifacts of the synthetic data that like would be obvious that the models are generating or not generating?
I think the 8B and the 7dB, I looked at the data and like I would not be able to tell them apart in a blind test. They're like super similar.
Okay.
But maybe there's like a hidden data quality that I'm not missing out on. The 1B and the 3B like were noticeably
like it doesn't make sense, or like
they're shorter, doesn't make sense, dropping like a lot of details. I see that stuff. Yeah.
Do you do any control for how much diversity there is?
That's what I was gonna.
Yeah. So I've done these rephrasing experiments with low temperature and high temperature. So this is a temperature 1. And I've done this with like smaller temperature, like 0.7 or something like that. The slope and it asymptotes out also as well. So you do need some diversity. You probably could get even more performance if you do even more diverse synthetic data generation. But I think like it's pretty encouraging over here that you're getting like 1,000 rephrases and you're still getting good performance over here. Like temperature 1 ends up being enough diversity for this task, but probably not enough for like the MMLU task.
One thing I'm thinking is like, so you're saying that we get hit some limits of self-improvement. Like, do you think it's because the model is not like still considered as an environment? Like, is it like if you send it to open world or like say Google search and get like that what's Internet Explorer, like if it can be like if it can get like more access to information, and like is that the next goal with synthetic data then? Like I guess like the thing is that you're still like you learned a new chapter but you're still in the same class. It's almost like you're in school but you're doing the same class again and again, and that's what you're not doing, right?
I think that there's maybe like an augmentation algorithm that has like some I think you could like natural curriculum to it to like make it harder or something. I'm not sure what that looks like, but it's like unclear to me. Rephrasing is not going to work. Maybe like crawling the internet like looks like this RAG baseline, which is like you retrieve documents, you train on it. I think that would give you like a fixed improvement. It would be really nice if like now this model can go out and RAG and get an even higher performance, but I'm not optimistic about this. That's also a true way to get self-improvement if that works, but I'm not sure if it'll work. So, but I think that there's definitely some algorithmic work to find the true self-improvement algorithm.
Are you suggesting something like you take a document to rephrase and then you search other related documents to bring into that context?
Here, what they're like, I guess the RAG over here looks like for every MMLU question, like go on the like this database which has the answers, or not the answers, but like documents that contain the answers, retrieve those documents, put them in context, and then like the training over here would be distilling, like RAG distillation, like distilling your model to behave as if it had the RAG documents in context. So like you train the model, just given a query, to match query plus the RAG documents.
Gotcha.
that's one way to train a model to be better and to like internalize this. And maybe if you set that new model out into the environment and to rank more, it'd get even better performance, but it's like not obvious to another way.
All right, thank you so much.
Thank you.
Thanks again.